central atom and then the terminal atoms. And then the most important things, I should have started here first, is you have to add up the number of valence electrons. So in carbon dioxide, carbon has 4 valence electrons, and then you have 2 oxygens, suited with 16 valence electrons. Anyway, you draw a single bond from the central atom to the terminal atoms, and then you fill the octet for the terminal atoms. Right? And then you check the central atom to make sure that it's a full octet. In this situation, carbon does not have a full octet because it only has 4 electrons being shown in the diagram instead of 8. So that is when, if you recall, we come in and we make a double bond. Is that ringing a bell? So you should have 2 lone pairs on the oxygen and 2 double bonds for the carbon. You may have any questions about that. Okay? Yes, ma'am? Because this is CO2, there are 2 oxygens and each of them have 6 valence electrons. The first step in finding how to draw a Lewis structure is out of the valence electrons, right? Yeah. So if you forgot how to do valence electrons, it's the ones place of the group number. Is that ringing a bell? Yeah, and then water, I had a lot of people put 2 O's and an H. No. No. Here's water. And remember, water has 2 lone pairs, and that's why it's bent instead of tetrahedral. All this is going to be on your final and your SGM, which is a new slow. Like all the stuff that you think you don't need to know anymore, you still need to know. But anyway, this one's linear, bond angle 180 degrees. This one's bent less than 109.5. Ring a bell? Cool. So sulfur dioxide, everybody always has trouble with that one. Sulfur goes in the middle. The number of valence electrons are going to be 18 because you have 6 and 6 and 6, which gives you 18. So I'm going to fill the octet for the terminal atoms. And then I have 16 and I need 18, so 2 go on the central atom. Then I check the central atom and I see that it only has 6 electrons, so I must move the lone pair and make.
Wow.
I hit the wrong button.
Is it like a back button?
No.
Wow.
Not at all. This is different than the other board that I use.
You should sue.
Whatever.
What if you were looking on
What I was saying was I had 2 extra, so I put them on the central atom, and then I'm going to make a double bond. So sulfur actually has a lone pair and a double bond. And so sulfur dioxide has it's a bent shape as well. And then methane's pretty chill. Right. And that's it. Remember, hydrogen has a full octet with only 2 electrons because it'll have the electron configuration of helium, which only has 2 electrons. How you feeling? It's good. The difference between endothermic and exothermic. Can you tell me the difference between endothermic and exothermic, please? Cora. Yeah, so you're definitely, that's pretty accurate. But endothermic reactions require energy to occur. Exothermic reactions release energy when they occur. Okay? So that's the thing. The reason why I got you guys to play with magnets, so these magnets on the table here, I need you to talk in your group, and I have magnets stuck together, right? Would be, I would want to break those apart maybe. So one of those, either magnets coming together or magnets getting split apart, one of those is endothermic and one is exothermic. Energy has to be put in or energy is released. So we're going to talk today about, and I'm going to do this on purpose this time. We're going to talk, we're going to talk about the enthalpy of a reaction, so the delta H of a reaction. And if it's negative, that's exothermic. And then if it's positive, if I have a positive change in enthalpy or energy, enthalpy means energy, then it's endothermic. Okay? So thinking about those magnets, would breaking them apart be endothermic or would it be exothermic? So talk to your group and figure it out. Breaking them apart, endo or exo? Okay, so tell me, breaking the magnets apart, Cora, I picked you again. Is that endo or exothermic? do you think it would release energy for me to pull these magnets apart? So, if energy is going to be released when I pull these magnets apart, but when I take my hands and I do this, did I have to put energy into it? Yeah, I totally did. To break magnets apart, and so atoms are held together by the same forces that magnets are held together. They're just held together by electrostatic attractions, right? Coulombic attraction. So anyway, these are held. I thought I dropped my magnet. Anyway, so it actually takes energy to break bonds, right? They'll stay like this forever unless I put energy into the system. Now, if you look close enough, if I put these magnets down on the table and I put them close enough, so they did that by themselves. Did you hear that sound when they came together? So that's actually literally energy being released through compression of airwaves, compression of air molecules through sound waves. Like that's why you heard it. There was energy released in the form of sound.
Yes.
So when bonds are broken, that will always, 100% of the time, always need energy. So when your biology teacher told you that when you broke down glucose, it releases energy, that's wrong, and I'm 100% right. But what ends up happening with glucose is the whole process of respiration. When you look at all the steps, there's cycles, and it has multiple steps. That ends up overall having a negative enthalpy, energy is released. But breaking bonds of anything, absolutely. There's nothing you can break apart that atoms are set together that releases energy. You will always have to take energy to pull those apart. Isn't that interesting? Yeah, but so here's the trick. As new bonds are formed, sometimes the difference in energy ends up being negative. So that's what we're about to go into. So again, when we do math here in a minute, because the formula is kind of crazy. When we do the math where bonds broken and bonds formed, if the positive number is bigger, right, and I get a positive value, that means energy has to go in. If I end up doing math and I get a negative answer, it's exothermic and energy came out. Do you understand that part? Because it would be a terrible time to be on your phone. The worst time ever. All right, cool. So let's go to the PowerPoint, which is on the handout that you just got, right? I actually gave you a PowerPoint today because it has a chart on it. I'm not going to use it a whole bunch, but it has pictures, and that's helpful. Are you ready? Steady. Go. Okay, so this is what your paper looks like. So this is the delta H from bond enthalpies. So here's basically the formula, but it looks really intimidating. Okay, so let me break it down for you a little bit. So the enthalpy of a reaction, right, is equal to, that's sigma. Have y'all had math class? Haven't seen sigma notation? This little, that means add everything up. Like the tattoo on my wrist means I is equal to everything added up from 0 to infinity.
Whoa.
So it means I'm the sum of everything. So anyway, that's what sigma means. But basically in this situation, I'm going to have to add up all the energy from the bonds being broken, and then I'm going to subtract all the added up energies of the bonds being formed. And notice which one's negative. The negative, this is really plus and negative, right? But that's what it is. The negative numbers are going to be the energy released from the bonds being formed. Just like energy is released when that bond is formed between the magnets.
Yeah.
Isn't that nice? So people going into AP. Here is a compound. To break that bond, energy has to be put in. So this is the energy diagram, potential energy. Energy goes up. As the bonds are formed, energy is released. So this would be an exothermic reaction because the energy you start with is bigger than the energy you end with. And if you understand that and you like that, then that's AP chemistry. And if you don't take that class. But I like to do that because I know a lot of y'all are heading that way, right? Let me kind of scroll down. All right, so exothermic, again, we have a negative delta H. And for endothermic, we have a positive delta H. So we will always take energy to break bonds, but if there is more energy released when bonds are broken, it's exothermic. I circled that wrong, but I did it very enthusiastically. Can I try again? This is still a negative, delta H. But if more energy is released when bonds are formed, that's exothermic. If more energy is released when the bonds were broken, that's endothermic. So basically, we're about to have to do some math. The math is actually easy. The only trick is the first step is to look at the bonds. And to look at the bonds, you have to draw the Lewis structures. Yeah, so anyway, I gotcha, hopefully. Okay, so I'm about to do this problem. I'm going to start it on the PowerPoint. I'm going to do it on the side. You may want to do it on your whiteboard. It's up to you. So what's happening here? The first step when you do these is you have to draw the Lewis structures. So I'm going to put all my reactants over here. I'm going to use black. I think that will be a little better. So I'm going to put my reactants over here. There we go. All right, so reactants. And then products. If you look, I don't want to scroll back because it'll erase my writing, but if you look back at that formula I gave you, basically it's reactants and their bond enthalpies minus products. And it goes in order, so, reactants minus products. It goes from left to right. It works out. Anyway, I'm going to draw the Lewis structures for these. So in methane, I just did that. I made you do it. Do you notice how I have one methane? I'm going to draw one methane. And then if you look right here, I have two oxygens. So when you draw the Lewis structure for a diatomic molecule, the number of bonds is the number of electrons it needs. So for example, if you look at nitrogen into nitrogen gas, nitrogen needs 3 electrons to have a full octet. So nitrogen gas has this Lewis structure. Fluorine gas or hydrogen gas, both of those just need 1 more electron. So their Lewis structure looks like this. That's a quick cheat on how to do diatomic things. All right? Did you remember that? Maybe you do, maybe you don't. But now do you remember? So oxygen has 2 bonds, a double bond, because it needs 2 more electrons each. So see how I have 2 oxygens? I'm going to draw 2 oxygens. And then over here, I'm going to draw the Lewis structure for the products. We already did. Can you see why I made you do the warm-up, right? The long pairs don't matter, so I'm not going to draw them right now. But you already saw that it has that. And then water. There's the Lewis structure. Now, what we're about to do, before I even start doing the math, it's very simple. What I have to do is I'm going to take a peek. See how I have 1, 2, 3, 4 CH bonds? That means here in a minute, I'm going to have to go 4 times this. Okay? And then see how I have 1, 2 of these? I'm going to have to take this and times 2. That will be added up, and that will be on the left-hand side of that formula. Okay? Huh? Not really. You're just multiplying and adding. But I'm going to do that in a second. But then over here, for the carbon dioxide, I have 1, 2 of those bonds. So I'm going to have to take 2 of that. Now, this is going to be in the side where I'm going to subtract. Are you following me? Okay. No? So there wasn't a no, there was an O. You don't get it. All right, cool. Was you cool on this reactant side? I'm basically adding up the values for the bonds. Now, remember the formula was bonds broken minus bonds formed, right? Yeah. So the bonds formed are products. Products have the bonds that are formed. And so I have 2 of those. So here in a minute, I'm not even doing the problem yet. I'm just showing you what I'm about to do. I'm going to take 2 of those and add them to 1, 2, 3, 4 of these. I'm going to do the math now, okay? So here we go. All of this is about to go away. Did you get it? Okay, so for the CH4, so again, this is broken, all right, or reactants. I have CH, which is going to be 4 times 413 kilojoules per mole. And then on the O2, I'm going to have 2, oh, not O2, like that. I just kind of draw what bond I'm doing. 2 times 495. And it's kilojoules per mole. I'm just running out of room. So I'm going to multiply those and add them up. Okay, so go ahead. 2 times 495 plus parentheses 4 times. So for this side, I get 2,642 kilojoules per mole. Okay. Now on this side, if you recall, the carbon dioxide looked like this. So I'll have that bond, I have 2 of them. 2 times 799 kilojoules per mole. And then I have 4 OH bonds, because I had 2 waters. You still okay? So 4 of the OHs, 4 times 467. I'm going to add that up. So 2 times 799 plus, parentheses, 4 times 467. So that is 3,466 kilojoules per mole. At this point, like I already told you, this takes energy, it's positive. This releases energy, it's negative. So I'm going to go 2,642 minus 3,466. I ran out of room, so I didn't put my units. And it says negative 824 kilojoules per mole. Is that the worst thing that's ever happened to you? No? Yes.
Why don't you have 4 for oxygen?
Because if I look at the Bounced equation, there's only 2 of them. That is a 1 double bond. So that is this. I have 2 of those.
So it's not.
2 single bonds, absolutely not. My people going into AP, please, well, I don't have any single bonds up here. Like, I don't have that as a choice, KC. But my people going into AP, please notice the difference in bond enthalpy between a single bond and a double bond. As bonds become stronger, they like single to double to triple, the bond enthalpy, the amount of energy needed to rip those apart is going to be greater, because when you have a single bond, it's 2 electrons holding together. When you have a double, it's 4. When you have a triple, it's 6. And they're closer together too, so they're little magnets inside their atoms. The Coulomb contraction is higher. If you're an AP, go to an AP, that's great. If you don't understand what I just said, that's fine too. Do you understand how to do the math and then subtract? If it's reactants minus products, it goes in order. But I didn't want to, I can't sleep at night if I don't tell you why it's minus, okay? It's not just because it's a formula, it's because why. Anyway, now here's the cool thing. What kind of reaction is this? Remember our 5 types of reactions? You want to place what is it? Now, doesn't it make sense that it would have a negative enthalpy? Because you burned it. Doesn't it release heat? Did you get it? What I'm saying? I'm going to say it again. Okay. Do you understand that this is combustion?
Yep.
So combustion is burning something, right? Doesn't that release heat? It's exothermic. Oh, pretty cool, huh? Example 2 isn't super helpful, so I'm going to go ahead and I want you to try number 1 on the back side, and I want you to use your white